This is week 5 of basic science. We're going to talk about the composition of matter and the atomic theory of matter. The atomic theory of matter states that all matter is made up of small particles known as atoms. The term atom actually comes from a Greek philosopher, and the term in the Greek actually comes from a word which means indivisible or simplest form. The truth is that it's not indivisible, as you'll see in the very near future. An element is a substance that is composed of one single type of atom and that cannot be simplified into other more simple substances. A compound, on the other hand, is a substance that is composed of more than one type of atom linked together. Now, in rare instances, these atoms can all be the same as they're linked together, and examples of that are hydrogen gas and elemental iodine. But most compounds are composed of two or more types of atoms that are actually different from each other. A mixture is a combination of elements or compounds, and there are different types of mixtures that we'll be talking about. Every element consists of tiny particles called atoms, and it was initially thought, as I said before, that these atoms were not divisible. These were the simplest particles, and they could not be divided into any smaller parts. The atoms of any particular element all have identical properties, so all the atoms in an element are exactly the same. Now, different elements have different atoms, and these atoms are different from each other. So, for example, if you're talking about hydrogen gas and iodine, elemental iodine, the atoms in hydrogen gas are significantly different from the atoms in elemental iodine. And these two different substances have different properties. Atoms of different elements can combine with each other in specific ways, and when they do that, they form what is known as compounds. The chemical processes are a result of the rearrangement, combination, or separation of atoms. So anything that's called a chemical reaction, usually what occurs is the atoms are rearranged in some way, the atoms bind to each other or combine in some way, or a compound is broken apart into simpler atoms. Now, this is an old version of a table of chemical compounds or elements. Some of these actually nowadays we know are single elements, that is, they're made up of single atoms. Others, such as ethyl alcohol, are made up of various combinations of atoms. This also shows something called a chemical symbol, and a symbol is simply a shorthand way of representing an atom or molecule. So a chemical symbol is a unique abbreviation for each element. Now, in the old days, many of these were fairly strange looking, and it was difficult to remember these. The newer chemical symbols are very systematic, and in some cases, the symbol comes from their Latin term. In others, it just represents the first and second letter in their name. Now, as I said, it's been found more recently that an atom is not simple. It is actually made up of parts. So inside the atom are various parts. Inside the atom, there's a dense core, and this dense core is known as the nucleus. The nucleus is made up of protons. A proton is a particle in the nucleus that has a mass of one atomic mass unit and a positive charge. The other part of the nucleus is called the neutron, and a neutron is a particle in the nucleus that has a mass of 1 atomic unit but has no charge. The atomic number is a number that equals the number of protons, and it identifies an element. And when we look at the periodic table, you'll see the periodic table is arranged based on the atomic number of the elements. And the atomic number tells you the identity of any particular element. If the atomic number changes, then the element changes from one type of atom to another type of atom. An electron is a particle that's outside the nucleus that has no relative mass. That is, it has no mass compared to the proton or the neutron. It actually does have a mass, which is 1/1800th the mass of either a proton or neutron. So it's so small that it's considered negligible, and it's said to have no mass. The electron has a negative charge and balances the positive charge of the proton. Now, isotope is a term that identifies atoms that are the same element. That is, they have the same atomic number, they have the same number of protons, but they have different atomic masses and atomic weights. And these differences are due to different numbers of neutrons in the various isotopes. So, for example, iodine has an isotope called iodine 131. That means it has an atomic mass of 131, whereas normal iodine has an atomic mass of 126. So the difference between those two, they both have the same number of protons, but one has 5 more neutrons than the other one. Quarks are smaller particles that make up what is known as nucleons, and nucleons is a term that means either a proton or a neutron. So it's anything that resides in the nucleus is called a nucleon. And the protons and neutrons are made up of smaller particles called quarks. A quark can be positive 2/3 up and minus 1/3 down. And so you have two kinds of quarks. That is, there's one quark that's positive 2/3, and it's called up, and another quark that's minus 1/3 down. And the combination of these various quarks tell you whether you have a neutron or a proton. So each nucleon is made up of 3 quarks. So for example, if you have 2 up quarks and 1 down quark, you'll have 4/3 positive and 1/3 negative. So overall you have 1 positive charge, so you have a proton. On the other hand, if you have 1 up quark and 2 down quarks, then you have positive 2/3 and a negative 2/3, and you end up with a neutron. So 2 up plus 1 down gives you a proton, and 1 up plus 2 down gives you a neutron. And this just shows you how that works. You have each nucleon, either a proton or a neutron, is made up of the quarks. And you can see on the left is a proton. It has 2 up quarks and 1 down quark. On the right is a neutron, and it has 1 up quark and 2 down quarks. Now the connections between these quarks is something called a gluon. A gluon merely connects these quarks together. Now outside the nucleus, the electrons arrange themselves in shells, which are concentric layers of electrons that can be labeled with capital letters. And where the electron resides depends on the energy that the electron has. The closer an electron is to the nucleus, the less energy that it has. We've said this before, an ion is an atom that contains an electrical charge, and this electrical charge occurs because an electron either is gained or lost. Ions do not occur because of changes in protons. They always occur because of changes in electrons. So the electrical charge that occurs is an imbalance between the electrons and the protons, and it's due to either a gain or a loss of electrons. An anion is an atom that has a negative charge, and this occurs when the atom gains an extra electron or more than one electron. A cation is an atom that has a positive charge because it has lost one or more of its normal electrons. It's extremely important, so you need to make a mental note of this and keep it in your head, that the ions are always formed because of changes in electrons, and it never happens because of changes in protons, because ions are the same element as the atom they're associated with, but they have a charge because of changes in the electrons. This just shows how the various shells of electrons are arranged, and you can see as the letters go out on the alphabet, K, L, M, N, they get farther and farther from the nucleus. And as it works out, as they go out farther and farther of the nucleus, the electron actually has more inherent energy. Each shell is capable of holding a certain number of electrons. The innermost shell, the K shell, can only hold 2 electrons. The L shell, which is the next one out, can only hold 8 electrons, and then the next shell, the M shell, can hold up to 18 electrons. So it goes 2, then 8, then 18, and if you want to know the formula for this is the first shell it's 2n plus 2. So the first shell is n squared plus 2. So the first one is 1 squared plus 2 is 2. The next one is 2 squared, which is 4, times 2 is 8. The next one is 3 squared, 9, times 2 is 18. The next one is 4 squared, 16, times 2 is 32. So it's 2n squared tells you with each shell how many total electrons can be in that shell. Now, in terms of atomic measurements, the first atomic measurement is something called the mass number. And the mass number is the sum of the neutrons and protons. Remember, these are the two parts of the atom that have mass. And so that it makes sense that the mass number would come from these two parts. So if you add up the total number of neutrons and the total number of protons together in an atom, then you know what the mass number is. Remember, the atomic number was just the total number of protons that were in the nucleus. The mass of an atom in atomic mass units is approximately the same as the mass number. The reason I say approximately the same is if you actually look at the mass of a single proton and you multiply, let's say you have 8 protons and 8 neutrons, that's an element called sulfur. You have 8 protons and 8 neutrons. If you multiply 8 times the mass of the proton and 8 times the mass of the neutron, you end up with a number that's very close to, but not exactly the same as 16, which would be the mass number. The average atomic mass is the weighted average of all naturally occurring isotopes. And when you look on a periodic table, you'll see a number like for hydrogen, it's 1.0008. Okay, so the average atomic mass for hydrogen is that number. And that comes from probably 2 or 3 isotopes, the most common of which weighs 1, and a very uncommon weighs 2 or 3. And so this is a box that just shows how the atomic mass is the average atomic mass is calculated. You take the mass of the first isotope times its relative abundance, which comes in a percentage expressed as a decimal, and multiply those two together, and then add to that the next naturally occurring isotope mass times its relative abundance. And that's where the average atomic mass comes from. So here's an example. You have the two naturally occurring isotopes of silver. Ag is silver. The first one is Ag107, which has an atomic mass of 106.90509, and it is 51.86% in abundance. The second one is Ag109, which has the mass that's shown in the table, and its abundance is 48.14%. So if you take 0.5186 times that mass plus 0.4814 times that mass and add those two together, you get the atomic mass that's probably shown in the periodic table.